Hi, my name is Charese Gates, and today I will be discussing the role of tectonic plates in the formation of new land masses. In this presentation, I will explain how the movement of Earth's tectonic plates create new land through processes such as seafloor spreading, volcanic formation, and continental collision. I will also reference the textbook science concepts and 3 AI-based resource summaries that supported my research. Here are my resources that AI gave me. So what are tectonic plates? Plate tectonics. Plate tectonics is a scientific theory that Earth's litmosphere is divided into rigid plates that move slowly over partially molten asthenosphere. The movement is driven by internal heat and mantle convection. Parsons and Richardson, 1980, explains that plate motion is controlled by largely by cooling and thickening of the ocean lithosphere as it ages, which means Earth's surface is divided is dynamic rather than fixed. Plate tectonic framework helps us understand earthquakes, volcanoes, mountain building, and creation of new crust. As the plate interacts, they either separate, collide, or slide past one another, producing different geological outcomes. This theory provides the foundation of how land masses are created over time and is the basis for every process we will look at moving forward. The diagram shows a subduction zone boundary where the oceanic plate is being forced beneath continental plate. This illustration highlights key features such as ocean trench, lithosphere, and asthenosphere and Benzoff zone, along with shallow and deep earthquake locations. So how plates move. The theory of plate tectonics developed from early ideas of continental drift. Though Alfred Wenger first proposed the continents once fit together like puzzle pieces, the mechanism was not understood until the seafloor spreading and the mantle convection were discovered. Stern, 2007, explains that modern tectonic plates emerged during the 1960s, unifying continental drift and seafloor spreading onto a single dynamic framework. Evidence such as matching fossils across continents, magnetic stripping of the ocean floor, and global earthquake patterns help confirm this theory. Today, plate tectonics is a widely accepted as driving force behind Earth's geological evolution and land formation process. This image displays 3 major plate boundaries side by side. The first one is divergent boundary. These pull apart, forming a ridge with rising magma. The second one is convection boundary. These plates collide, forming trenches, volcanic arcs, and earthquakes. The third one is transform boundaries. These plates slide past one another, generating earthquakes. It also shows the lithosphere and asthenosphere, volcanic activity, earthquakes, and directional arrows indicating plate motion. Land formation and divergent boundaries. One major process that creates new land seafloor spreading. This occurs as divergent boundaries or plates move apart, allowing magma to rise from the mantle. As it cools, it forms a new ocean crust. McDonald, 1989, notes that mid-ocean ridges are continuous volcanic systems where the new ballistic crust is generated and pushed outward. Sinton and Derrick, 1992, further describe that active magma chambers exist beneath spreading centers, providing a molten source of crust formation. Over millions of years, this process expands ocean basins and slowly creates new seafloors, serving as a conveyor belt for crust generation. The image is divided into 3 stages. The first one, a rift valley stage, continental crust being pulled apart, magma rising below. The second stage is new ocean basin stage. Ocean water fills the rift as spreading continues. Magma forms new crust. The third stage is mature ocean stage. A mid-ocean ridge develops, sediment accumulates outward over time. You can see little magma upwelling, lithosphere thinning, and the ocean crust creation, which visually confirms ongoing land formation at divergent boundaries. Volcanic islands and hotspot activities. Mid-ocean ridges and underwater mountain chains formed by rising magma at the spreading boundaries. As magma erupts and cools, it forms new crust along the ridge axis. McDonald's 1989 explains that the final scale volcanic and tectonic activity continuously renews oceanic crust with the ridge environment, demonstrating ongoing land creation. Sinton and Derrick 1992 also found that melt lenses beneath ridges feed eruptions, confirming a constant supply of magma necessary for crust formation. These ridges are along mountain systems on Earth and play critical roles in building new lithospheres. The image shows the mantle plume, which is a hotspot, pushing magma upward through the lithosphere, forming volcanic islands. As the Pacific plates moves northwest, other islands are positioned further from the hotspot, while newer islands sit directly above it. The zone magma generation shows where eruptions originate. Land formation and convergent boundaries. Volcanic islands form when tectonic plates move over stationary hotspots. The mantle plume remains fixed, while plates slowly glide above it, creating a chain of volcanoes over time. Craig and Saran 2014 state that the Hawaiian volcanoes grow from rapid ballistic eruptions that accumulate and eventually emerge above sea level. As other islands move away from the hotspot, new ones form in their place. This process is visible in the age progression of the Hawaiian Emperor Sea Mountain chain, which also helps scientists measure plate motion. This cross-section diagram displays the mantle plume beneath Hawaii. With rising magma through the lithosphere to create volcanoes, the islands are labeled with ages younger near the hotspot and progressively older as they move away, confirming plate motion direction. Real-world examples of new land forming. As at convergent boundaries, plates collide and either subduct or uplift. If oceanic plates subduct beneath the continental plate, magma forms and rises to create volcanic arcs. Belick and Lay 2019 emphasize that subduction zones generate magma thrust earthquakes and arc volcanism, contributing to crust growth and deformation. In continental collisions, neither plates subduct easily. In continental collisions, neither plates subduct easily, so land uplifts to form massive mountain ranges. This is how the Himalayas were created. Over time, convergent boundaries build significant amounts of new land through volcanic rock accumulation and crust thickening. Real-world examples of new land forming continued. This slide contains 3 real-world geological examples. So this is Iceland divergent boundary. The image shows Iceland located in the mid-Atlantic range where 2 tectonic plates pull apart. Volcanic fissures and speeding zones are visible, demonstrating active crust formation at a divergent boundary. The second one is Hawaiian volcanism. The ocean floor image shows that the Hawaiian island chain and the seamount formed at the Pacific plate moved over the stationary mantle hotspot. This visually represents volcanic island growth. And the third one is the Himalayas. This is a convergent boundary. The mountain image shows the Himalayas created when the Indian and Eurasian plates collided. This demonstrates continental uplift and mountain building through convergence. The growth of a new island over time. We can see tectonic plate formation happening today. In Iceland, the mid-Atlantic ridge emerges at the surface and land grows where plates diverge. McDonald, 1999. In Hawaii, volcano activity form hotspots form new islands. In the Himalayas, continental collision continues to uplift the mountain range. Uden et al. 2020 also observed new island growth and long-term coastal expansion in the Bay of Bengal, demonstrating that land formation can be measured in human timescale when sediment and volcanic material accumulates. This image demonstrates several new ways land grows over time. At the ocean spreading center, magma forms new crust as plates move apart. Hotspots gradually build volcanic islands through repeated eruptions, while continental rifting can eventually create new ocean basins to form mountain ranges. These processes occur over millions of years and show how Earth's surface is always developing. Why new land formation matters. Land growth is slowly but a continuous process. Mid-ocean ridges expand the sea for millions of years. The volcanic islands grow through repeated eruptions and sediment-rich coastlines built outward through deposition. Uden 2020 explains that found that new land masses formed and expanded significantly over 30 years, demonstrating measurable growth. Combined with hotspot volcanism and convergent uplift, Earth is continuously generating new land at different scales and speeds. The image shows 4 possible ways continents could merge in the future. It highlights why land formation matters. New land creates fresh ecosystems, shifts climate and ocean accumulation, and changes where resources and human settlement can exist. As tectonic plates move, the Earth we know today will look completely different in the future. This demonstrates long-term importance of ongoing land formation. My conclusion. In summary, plate tectonics is responsible for building new land through seafloor spreading, mid-ocean region volcanic hotspot, and convergent collision. New crust forms where plates diverge. Volcanic islands grow from hot spots, and mountain belts rise when plates collide. These processes operate continuously and shape Earth's surface over geological time. Thank you for listening, and now we will look at the research references to use to support this presentation. So here are my references.